So this is the final project presentation, and we chose to do a project on California Road Network Datasets. Okay, so our leading question was that we wanted to find the most optimal path between 2 points in the California Road Network Dataset. And our goal was to create a practical program that optimizes travel, a simple but common real-world problem that many people experience. Um, we planned on formatting the data by using nodes to represent the intersections and edges to represent the roads, and we stored the edges as pointers to other node objects. Since the dataset might have errors, we plan on testing the data to verify that it's being read correctly. If an error in the data is found, we will have removed affected nodes and edges from the dataset. For the traversal, we also plan to implement a BFS traversal, and for the covered algorithm, we calculated the shortest path between two nodes using Dijkstra's algorithm. This algorithm takes in two nodes and returns a vector of the nodes visited on the short path. Our runtime goal for this algorithm was O of n squared, where n was the number of vertices. For the uncovered algorithm, we planned on implementing a landmark path algorithm that calculates the shortest path between three nodes. This algorithm takes in three nodes and returns a vector containing the nodes visited on the shortest path between them. Our goal for this algorithm was to minimize the runtime.
So I'll be talking about the development and challenges of our project, starting with the development. So whilst developing the various parts of the design of our projects, we had to concentrate on the following. The graph reader. The graph reader is responsible for reading in and storing data from a .txt file. Nodes from the data file are stored and returned as a vector of integers. Undirected edges are stored and returned as a vector of int pairs. This was implemented in graphreader.cpp and graphreader.h. Next is the graph. The graph itself, in .cpp and .h, we created a graph from a vector of edges that contains a method which calculates the shortest path between two vertices, a method that calculates the landmark path, and a method that runs a BFS traversal. The next was the traversal. The traversal, we did the BFS traversal using Dijkstra's algorithm. This was implemented in graphtraversal.cpp using an iterator. Continued, we had the test folders. This test folder included test.cpp and sample data sets as .txt files. Included tests for the graphreader.cpp, the graphtraversal.cpp, and the graph.cpp. They're separated by different sections. So this was where we tested if our code actually worked and if we needed to change anything. Data in the folder should only be the data sets used for testing. Nothing more, nothing less. Next is the data folder. This contains any data that can be used for the executable. Next is the results folder. This contains results from running the main executable that could be stored in the results folder. And last but not least, the MD folder, which we stored a development log, group contracts, goals, project proposal, and the like. So that was it for development. Now I'll be talking about the challenges of our group projects. Firstly, the fact that we could not be physically present amongst each other due to the pandemic made working on this project a little bit difficult, but we overcame this by creating a Discord group and using Zoom. That Discord group proved to be very, very useful. Next, we had a bug in the shortest path function that only showed up when we tried to run it on the full dataset. So it didn't show up on individual test cases, but when we tried to run it on full datasets, then it showed up. So we were confused as to why it was passing test cases individually, but as a whole, it wasn't. Another challenge was making the graph reader to be efficient enough to work on the full datasets. Another major issue was understanding how we're going to implement the iterator, which our mid-project check-in advisor helped us with in choosing a BFS traversal and in understanding that we had to work with Dijkstra's algorithm to get the iterator to work. So that was it for challenges.
And now for our conclusion. For our final project, I'll record functions that we implemented, which include the shortest path algorithm, landmark path algorithm, as well as the BFS traversal, worked as expected on both small and large scales. We verified this by running all of these algorithms on both a medium-sized graph as well as the entire datasets of the California roads. All tests that we wrote passed, including various edge cases for all of our functions. Additionally, the program worked properly and was easy to use. We made sure that it was easy for different graphs to be read in, as well as easy to pick various output file saving locations. And finally, all runtime goals were met. And now for the goals of our final project. Our main objective for this final project was to make a program that gave useful and meaningful outputs about a road network. By using degrees for weights, we were able to calculate direct paths between locations that could be used to travel the road network. Since our functions worked as expected, as stated in the previous slide, as well as provide useful data, we concluded that our original goal for our project has been met.
Now for our likes and dislikes. We liked working on real-world data. We felt that it was more practical and useful for the future than working on some data set that would only be for this specific project and did nothing else. We liked being able to pick our own data and algorithms. It allowed us to choose something that we were interested in, and it made it really flexible into like what we wanted to do, which helped us stay motivated for the project. We liked having a midpoint check-in. It was really useful to have a check-in where we could ask questions and make sure that we were on the right track to finishing the project. Now for our dislikes, we disliked the overlap between the last MP and the final project. It made us behind the schedule that we originally planned, and we weren't able to get as much work that we would have liked during that week. We also disliked learning about the covered algorithms late. Again, it made us behind schedule. If we had more time, we would implement more complex algorithms. Road network is definitely a straightforward algorithm, but there's definitely more complex algorithms you can do with it to solve everyday common problems. We would improve edge weights. Because our dataset didn't come with edge weights, we based ours off of the degrees of the vertices of the edge, but we could definitely find different weights to use with different algorithms. We would improve efficiency of our algorithms. We could also improve user interface with our executables to make it a lot more easier to use. And we would add more thorough tests to ensure that everything worked correctly, even in different circumstances that we might not have thought of.